Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 7. Generalized Eigenvalue Problem. The generalized eigenvalue problem is a more complex version of the standard eigenvalue problem, and it typically arises in the following form. Where A and B are square matrices of the same size, X is the eigenvector, and lambda is the eigenvalue. The matrix A is typically symmetric, but B does not necessarily have to be symmetric, although in many cases, it is positive definite or at least symmetric. The Cholesky decomposition is applied to the matrix B when it is symmetric and positive definite to transform the problem into a simpler, standard eigenvalue problem. This approach allows for more efficient and stable numerical solutions by reducing the complexity of the general problem. Transforming the generalized eigenvalue problem to standard eigenvalue problem by multiplying both sides with the inverse of matrix B. The resulting inverse B-A product matrix will not necessarily be symmetric even if A and B are symmetric. To overcome this hurdle, matrix B is decomposed as LL transpose, where L is a lower triangular matrix and LT is its transpose, found by Cholesky decomposition. Note that all eigenvalues of a positive definite matrix are positive. Also, a diagonally dominant matrix with positive diagonal elements is positive definite. Left multiplying the right-hand side of the eigenvalue problem with inverse L and substituting B equals LL transpose gives, since inverse LL equals identity matrix. Similarly, left multiplying AX product with inverse L and making use of the transpose of inverse L equals inverse of transpose L identity yields. Where transpose of inverse L is denoted by L to the minus T and L to the minus T times L to the T gives the identity matrix. Combining these expressions, we find where the triple matrix product inverse L, a transpose of inverse L, is symmetric with the same eigenvalues as the generalized eigenvalue problem. By setting C equal to the triple matrix product, inverse L, a transpose of inverse L, and Z equals transpose L times X, the problem is reduced to a standard eigenvalue problem in the transformed space, where the matrix C is similar to the original matrix A, and the eigenvalues remain unchanged. However, the eigenvectors are transformed by the matrix L. This standard eigenvalue problem can then be solved using any standard eigenvalue solver. Subsequently, the original eigenvectors can be determined from X equals transpose of inverse L times Z. The procedure to determine the lower triangular matrix L is called the Cholesky decomposition and covered in section 2.8. Although we can use a standard matrix inversion algorithm to find the inverse of a lower triangular matrix, we prefer to use a specific approach adapted to triangular matrices. An inversion algorithm tailored to a lower triangular matrix is faster and more efficient because it avoids working with elements with unnecessary zeros. The inverse of matrix L can be found as follows, where the -1 as the exponent denotes the ith row and jth column element of the inverse matrix L, not the algebraic inverse. The advantages of the Cholesky decomposition in this context are: Cholesky decomposition is a numerically stable and computationally efficient method. its memory requirements are considerably less. It is highly adaptive to parallel architectures. Therefore, pivoting is not required. It is faster than the LU decomposition as it exploits the symmetry of the matrix. It can be used for solving linear equations with symmetric positive and definite matrices. It requires half of the number of operations required by Gaussian elimination. A disadvantage of the method is the method does not work for any matrix, except for symmetric positive definite matrices. Now let us consider the following generalized eigenvalue problem. We would like to transform this problem into a standard eigenvalue problem. Matrix B is symmetric. It can thus be decomposed using the Cholesky algorithm. Without going into the details of it, we will provide the lower triangular matrix as follows. We need the inverse matrix of the lower triangular matrix. We begin by working with the first row and first column, and work our way down. The diagonal elements of the inverse of matrix L are the reciprocals of the diagonal elements of the lower triangular matrix. This step is straightforward because the diagonal is independent of the other elements. After handling the diagonal, we move down through the matrix. For each off-diagonal element in the inverse, we use the information from previous rows to solve for the unknowns. In each row, we start from the unknown element on the right and move to the left until we reach the element in the first column as we find the unknowns. The same process is repeated row by row, using known values from previous rows to solve for the unknowns in the current row. By working in this way, we are progressively eliminating the non-zero entries of matrix L, ultimately arriving at the inverse. By the time we exhaust all rows, we fill in all the values in the inverse matrix, and it does have the same lower triangular structure. The matrix C of the standard eigenvalue problem is constructed as follows. Finally, we have the standard eigenvalue problem. The eigenvalues of matrix C and the product of the inverse matrix BA and the generalized eigenvalue problems are identical. However, the eigenvalues of the original problem must be evaluated by the transpose of the inverse L times the eigenvalues of Z. With this note, we conclude this lecture. That is all for now. See you next time with another topic. Bye.